Alright, hello everyone and welcome back to another video. I'm going to show you just how easy it is to run a quantum chemical calculation on your laptop or computer. Okay, so let's jump straight into it. We're going to be optimizing the geometry of a single water molecule today, and to do that we'll be running a Hartree-Fock calculation in the Orca program. Now, Orca is a freely available, open source quantum chemistry package that you can download for Linux, Mac, or Windows like I'll be doing. Here's the website of the Orca forum where you can sign up and accept the user agreement. Head over to the downloads page via the link up here. In my opinion, Orca is one of the easiest to use quantum chemistry packages available, but one thing you should know is that it's entirely command line based. You interact with the program through text. Text goes in, text goes out, input to output. In practice though, it's very convenient to use another program to help us prepare input files and analyze the output. And for that, I'm going to be using Avogadro, another great piece of cross-platform open source software. You can of course find all of these links below in the description. Alright, so once you've got those downloaded and installed, you can go ahead and open up Avogadro by pressing start and beginning to type AVO. Avogadro has this useful toolbar at the top. This window on the left has various options for the tool that you've currently got selected. We'd like to use the draw tool, the pencil icon on the far left, and select oxygen from the drop-down menu here. Then I'm going to uncheck the adjust hydrogens and build our water molecule one atom at a time. The first atom is easy. We simply left click anywhere in this black box. Now if we select hydrogen and then left click, it'll turn into a hydrogen atom. That's not what we want, so Ctrl Z to undo. We like to click and drag with the left mouse button, leaving the oxygen and creating a bond to a hydrogen atom. Now we'd like to add the second hydrogen to complete our H2O molecule. We expect a V shape for water, and it's always best to start with your best guess for the input structure. Okay, now we're going to save these XYZ coordinates so that we can use them in our Orca input. I've made this folder on my desktop, so I just click XYZ from the file type and call it imp.xyz. If we navigate to this folder, right click, open with Notepad, we can open this file and copy the list of atoms with their atomic symbols and XYZ coordinates. Now we need to prepare the input file for Orca, so we hit File, New. The so-called simple input line, where you write your main Orca keywords, begins with an exclamation mark. Now we need to say what kind of calculation we'd like to perform, and we would like to ask the program to find the equilibrium structure of water, which means finding the combination of nuclear coordinates with the lowest energy. So it's an optimization problem, and the keyword is opt. You've also got to specify the theory with which the energy should be calculated. As I mentioned earlier, we're going to be using Hartree-Fock theory today, so the keyword is HF, and the specific variant is known as HF3C. It's a great method and it's implemented very well into Orca. Now we're almost ready to add the coordinates from Avogadro. This section starts and ends with an asterisk. Then we write our XYZ to let it know the format, and now we write first the charge and then the spin multiplicity. The charge of our neutral water molecule is of course 0, and the spin multiplicity is equal to the number of unpaired electrons plus 1. All of the electrons in water are paired, so that's 0 plus 1, and it's just 1. Okay, we're finally ready to paste in the coordinates on a new line and finish off this section and the entire input file with another asterisk. Now we save this in the same folder as before. You can call it anything you like, so I'll call it orca.imp. Now we're all set to run our first Orca calculation. I press start, type CMD to open up the command line. To run our calculation, we first need to navigate to our water folder. On the command line, I type CD, space, and right click to paste in the path. Enter will execute this command and take us to the right folder. It's a bit of a different way of interacting with the computer than you're probably used to, but I promise we just need one more command and we're all done. Okay, now I type the name of the program, Orca, then the name of the input, orca.imp, then a pointy bracket, to request that all of the output should be written to a new file, which we'll name orca.out. Okay, we press enter again and we can see that various temporary files are being created and destroyed, which tells us that the calculation is running. Water is a small molecule and the 3C methods are very efficient, so it should just take a few seconds. Seems like it might already be done. We can check that by opening the orca.out file, which remember is just a text file, by right-clicking, open with Notepad. If we scroll right down to the end, we can see this beautiful message telling us that the program finished normally, so we know that the calculation didn't crash. Another way to verify this, to be extra sure, is to hit Control F and then type hooray, which should take us to this message where Orca confirms that the geometry was indeed optimized. Now finally, if we open another Avogadro window and drop in the orca.xyz file, we can visualize the optimized geometry. Now comparing to our initial structure, we see that I considerably overestimated the OH bond distances, but the program has adjusted this to what it calculated to be the equilibrium structure. Alright, there you go. If you have any questions, then please leave a comment. If you enjoyed the video, you're welcome to leave a like, and subscribe if you'd like to see more computational chemistry tutorials. Ciao! Thank you.